We're going to return to mathematical induction. We saw it, of course, last year, but now we're looking at a topic on proof. Makes sense to talk about induction as it is a style of proof. Let's remind ourselves of the different types. Series types was the first type we looked at. I'm going to do this. I'm leaving it in some notation this time. We're going to prove that the sum, and there's our general term, going from 1 to n, always equals 1 minus that fraction there, 2 on n plus 1 times n plus 2. Okay. Our first step is to prove it true for the first case. The first case in this case is 1. Left hand side, sub into our general term. The first term is r equals 1. Sub it in, we get 2/3. Right hand side, sub it into the supposed formula. And it does work out to be 2/3. So yep, it certainly works. The left hand side of this is the same as the right hand side. So hence, it does work for 1. Our next step was now to just assume what we're trying to prove is correct. So I'm going to assume it's true for n equals k, where k is some positive integer. But always write down your assumption. Remember, you're writing a proof not for you, it's for someone else. So they need to know what your assumption is, so you write it down. Notice when you're in sum notation, the r's are still r, that hasn't changed. It's just that I'm going to k instead of n, and then on the right hand side I have k instead of n. We're going to prove it true for the next case, which is k plus 1. Again, write down what you're trying to prove. So whoever's looking at your solution knows what you're doing and knows when you get there. In sum notation, again, the general term has not changed. That's still 4 on r plus 1, r plus 2. What has changed is we're now going to k plus 1, and on the right hand side, that changes. It should now be in the denominator, k plus 2, k plus 3. Well, the series type, we set it up where we say it's the sum to k terms, which I've got here. I've actually put it as the second thing there. And then the k plus 1th term I've just pulled out. The k plus 1th term will be 4 on k plus 1, k plus 2, k plus 3. We then substitute in the assumption, and we want to create the right hand side of what we're trying to prove. Now, we've already got the 1 there, so I'm just going to leave that alone, because there's no point putting that into the fraction if I've then got to take it out of the fraction again. But we've got to be really careful when we combine these two fractions, because I want minus, because you have a look at what we're trying to prove, it says minus. So I want the minus out the front of the fraction. So it's actually this positive fraction that becomes minus 4. The other one, the denominator is different, so I've multiplied the 2 by k plus 3. Alright, let's see if we get, well, logically, looking at where we're heading to, I should end up with, what's it going to be? The k plus 1's got to cancel, so I should end up with 2k plus 2. 2k plus 2, which nicely factorises to be 2 outside of k plus 1. K plus 1's cancel, we get the result we're looking for. Remember, this part of the induction proof is actually a deductive proof, so we should be concluding with our if-then statement. Hence the result is true for n equals k plus 1 if it is also true for n equals k. I've sort of written the if-then the other way around, but it's still an if-then statement. Now we can induce the solution, we pull it together, and since it's true for n equals 1, then we can now induce it to be true for all the others. So it's going to be true for all positive integers by the method of induction. Okay, so that was our series type. Here's one that's a little bit different. It actually was an Extension 1 paper back in 2004, because they did more interesting ones in Extension 1 back in the old course. Now these interesting ones seem to be reserved for Extension 2. Use induction to prove this one. It's still a series type, but instead of adding terms, we're just multiplying terms, but still the same idea. So I'm going to prove it true. First case is n equals 3, however. So prove it true for that. Left-hand side becomes 1/3. The right-hand side, also 1/3. So yeah, it does work for n equals 3. So my assumption is going to be true for n equals k, but this time where k is greater than or equal to 3. So there's my assumption. Prove for the next case, k plus 1. And that's what we're now going to try and prove. So let's start with the left-hand side. Same idea, I'm going to rewrite it, the last term, and well, it's not a sum now, it's a multiplicative sum in a way. But that's our assumption. We can sub in for it. There we go. Now we just have to play with the algebra to get the result that we're looking for. Got to turn it into all one fraction now, so it's 1 minus 2 on k plus 1. K plus 1 minus 2 is k minus 1. Oh, that cancels with a k minus 1. 2 on k plus 1. That is what we're trying to prove. Hence it is true for k plus 1, if it's also true for k. And then since it's true for n equals 3, then it's going to be true for all integers greater than or equal to 3 by induction. Okay. Divisibility type. Prove that n squared plus 2n is a multiple of 8 if n is even. So again, this is a bit different to the extension 1. Extension 1, they're always just nice positive integers. Here we're saying, n is going to be an even number. So the first case will now be n equals 2. That's the first even number. 2 squared plus 2 times 2 is 8. And that is obviously divisible by 8. So yep, works for the first even number. I'm going to assume it's true for k, where k is an even number. So k squared plus 2k is equal to 8p, where p is an integer, and k is an even number. So that's the other part of my assumption. I'm going to assume k is an even number. Prove it true for the next case. Well, the next case will be k plus 2, because it's the next even number. So this is what I want to prove. K plus 2 squared is equal to 2 times k plus 2 is equal to 8 times some integer. Proof. I've got to get my assumption in there somehow. So I need to pull out k squared plus 2k. Well, if I expand everything out, you can see, well, there's a k squared in the first expansion, there's a 2k in the second expansion, so I can group those two things together, and I've got 8p. I'm left with 4k plus 8. Remember, we're trying to show 8 goes into this. Ordinarily, we'd say we've got a problem, because k on 2 is not an integer. However, in our assumption, we said k was an even number. And if you divide an even number by 2, you will get an integer. So that is true, but I make sure I make the point it's true because we know k is an even number. So hence it's true for k plus 2 if it's also true for k, since the result's true for n equals 2, and so on. Another way you could set that out, if I'll just take it from the assumption part, I could actually assume n is 2k. And again, k is just a positive integer. Well, that automatically makes n an even number. And so my assumption now would simply be 4k squared plus 4k is 8p. But now I'll prove it true for n equals 2k plus 2, because that will be the next even number. That's what I'm trying to prove. So let's prove it. Again, we've got to get our assumption in somehow, expand the whole thing out. 4k squared plus 4k, yep, I've got that there. Pull those together, they become 8p. I'm left with 8k plus 8, and we can see the multiple of 8 straight away doing it this way. Doesn't really matter which way you go, it's probably the same amount of working out either way. Now here's the big difference between extension 2 and extension 1. Inequality inductions. They don't do those in extension 1 anymore. Prove that 2 to the power of n is greater than n squared for all integers greater than 4. First case, therefore, is n equals 5. Left-hand side is 32, right-hand side is 25, and 32 certainly is bigger than 25. So true for n equals 5. So I'm going to assume it's true for n equals k, k is an integer, such that k is bigger than 4. In other words, I'm assuming that 2k is greater than k squared, but I'm also making the assumption that k is greater than 4. Now when we're doing inequality proofs, that second part can prove to be very important for the sake of the proof. Prove the result is true for k plus 1. So now I'm going to do it this way. I'm going to use the idea of inequality proof of I'm going to pull everything to one side, and I'm going to try and show this is always positive. 2 to the power of k plus 1 minus k plus 1 squared is greater than 0. That's what I'm going to try and prove. 2 to the power of k plus 1 minus k plus 1 squared. I want to get my assumption in. Remember my assumption, 2 to the power of k is greater than k squared. So I've got to pull 2 to the power of k. Well, I can do that. 2 times 2 to the power of k is 2 to the power of k plus 1. I'll also expand out the other bit. But now I can say, well, that is going to be greater than 2k squared, because I know 2 to the power of k was greater than k squared. Well, that is equal to k squared minus 2k plus 1. Remember, we're trying to show this is positive. But hang on. If k is greater than 4, then this expression would have to be greater than 4 squared minus 2 times 4 minus 1. Now why can I say that? I can say that because k is greater than 4. But I've got to be careful because of this negative. But because I'm only subtracting 2 lots of 4, I'm not going to get that 4 squared in the negative territory. Because 4 squared is 4 times 4, and I'm only subtracting 2 times 4. So this will still be greater than this expression. That's okay. If I was subtracting, say, 5k, I couldn't do it, because I couldn't guarantee that this is going to be okay. Well, that equals 7, and 7 is indeed greater than 0. Hence the result's true for k plus 1, it's also true for k. Since the result's true for n equals 1. We're going to prove this series type. It's 1 plus 1 on 2 squared plus 1 on 3 squared and so on is always less than or equal to 2 minus 1 on n. Didn't write it there, but for all positive integers. Prove the result's true for n equals 1. Left hand side we get 1. Right hand side we get 1. Well, 1 is less than or equal to 1. I mean, it's equal to, but that means it's less than or equal to. We got one of those, so yeah, that's okay. We will assume it's true. And we want to prove the next case. So that's what we're trying to prove. Again, I'm going to use the idea, let's try and show this is always, in this case, negative or equal to 0. Our proof, series type. So I will break it up into the sum to k and then the next term. This will allow me to sub in my assumption. So I can now say it's less than or equal to 2 minus 1 on k plus 1 on k plus squared minus 2 plus 1 on k plus 1. Well, 2 minus 2, that goes away. We'll create an algebraic fraction with the rest of it. So k plus k, k plus 1, and so on. Let's expand the top out. When we expand the top out and collect terms, we end up with negative 1. Now remember, we're trying to show this is always negative. Well, k plus 1 squared is always positive. No question about that. We have assumed k is a positive integer. So the denominator is positive. The numerator is negative 1. So yeah, that is always less than 0. The reason I know that is because k is greater than 0. That's a key point there why I can say that. I mean, the k plus 1 squared being greater than 0, that's obvious. But I probably need to note that I can do this because k is greater than 0. Hence the result's true, etc., etc., etc. Okay. The idea of induction, the actual idea of induction. Here's a really interesting question. 2 vertical walls and a floor meet at a corner. A cube is placed in the corner. A solid shape is then formed by placing identical cubes to form horizontal rows on the floor against the wall, or by stacking vertically. And there's an example of one such shape. N is going to be the number of cubes used to make the shape. We're going to use induction to show that the number of exposed faces of the cube is always 2n plus 1. Prove the result is true for n equals 1. Well, I'm going to draw a picture. There's nothing wrong with drawing a picture. That would be the case right there. If I'm just putting one cube. Well, I can see we've got 3 exposed faces. The formula tells me we should have 3 exposed faces. So yeah, that works for n equals 1. I'm going to assume the result's true for n equals k. So what am I assuming? I'm assuming that k cubes will have 2k plus 1 exposed faces. I want to prove it's true for k plus 1. So I want to prove that k plus 1 cubes will have 2k plus 3 exposed faces. How on earth do I do this? Again, I'm going to do it with pictures. I'm going to add a cube to this picture. What happens? Well, the addition of a new cube, whenever I put a new cube on, doesn't matter where I put it, under the rules that they said, we're going to cover up one of the existing faces. Okay? We will cover up one existing face. So it will become this. But it will now expose 3 new faces of the new cube that I've added. So I've subtracted one face, but I've added in 3 more faces. So I could say this: the number of exposed faces of k plus 1 cubes will equal the number of exposed faces of k cubes, how many I had, but I've taken one away and I've added 3 more in. Well, that's going to be 2k plus 1, that was my assumption, minus 1 plus 3, which is 2k plus 3. And that's what they wanted me to prove. So hence it's true for k plus 1 if it's also true for k. So it's still using the same idea of inducing the solution. We prove it true for k plus 1 if it's true for k. Since the result is true, etc., etc. Then there's these other ones, what's called a recursive formula. Now that's where one term is defined by using previous terms. You remember we saw it in series and sequences. If your recursive formula is defined in terms of m preceding terms, then what you tend to need to do is this. Prove it true for the first m terms. So whatever that happens to be. Then assume it's true for n equals k, k minus 1, k minus m minus 1, however many terms we've got. The recursive formula, one of the biggest mistakes is people try and prove the recursive formula. No, the recursive formula is a fact. It's given to you, so you can just use it. You don't have to prove it. A sequence is defined this way. A1 is the square root of 2. Then every term after that is going to be worked out using this formula. The square root of 2 plus the previous term. We're going to prove that every term is less than 2. Every term is less than 2. Okay. Well, there's only one thing I'm substituting into the recursive formula, so I only need to prove it true for the first case, which is n equals 1. They've told me that the first term is the square root of 2. The square root of 2, well, yeah, it was about 1.414 or something, but it's less than 2. So, yep, first case works. Assume it's true for k. So I'm going to assume that ak is less than 2. We now want to prove that ak plus 1 is also less than 2. Start with your recursive formula. So ak plus 1 will be the square root of 2 plus ak. Well, I can sum my assumption straight in now because we've assumed that ak is less than 2. So this must be less than the square root of 2 plus 2. Well, that's the square root of 4, which is 2. ak plus 1 must always be less than 2. Hence the result is true, etc., etc., etc. Far more fun when you have to substitute two previous terms in, and the most classic of all of those is our Fibonacci sequence, so let's do that one. The first two terms in the Fibonacci is 1, and you work out every number after that by adding the two previous terms. We're going to prove, the golden ratio, love it, that every term is less than the golden ratio to the power of n. I'm going to prove it true for both 1 and 2, because there's two things I'm going to substitute in. I'll prove it true for the first two cases. Now, the first case was n equals 1. A1 is 1. 1 plus root 5 on 2 is the golden ratio, 1.6, well, rounded off to 2 decimal places there. It's actually, what is it, 1.61? Anyway, doesn't matter. It is less than 1. It is less than 1. No, 1 is less than the golden ratio. Let's have a look at n equals 2, which also is 1, but the right hand side is now the golden ratio squared. Oh, it gets bigger. 2.62, so yeah, 1's still less than that. Yep, true for the first two cases. I'm going to assume it's true then for k and k plus 1. Need two assumptions because I'm going to end up subbing two things into our recursive formula. So I'm going to assume both of these things. Okay. Prove it's true for k plus 2. I'm again using the technique of moving everything to one side here. I'm going to show this is always negative. Start with the recursive formula. So ak plus 2 is ak plus 1. Sub in the assumption so it's less than this. Okay. I want to show that this is negative. There is a common factor there of 1 plus root 5 on 2 to the power of k, so I'll pull out the common factor. That is a positive number, no matter what k is. So hopefully whatever's in the second brackets is negative. It's this bit I want to show is negative. So 4 plus 2, 4, playing around with it, it's actually equal to 0. Well, what do you know? It's equal to 0. Well, we got it then, haven't we? So ak plus 2 minus that is less than 0. Hence it's true for k plus 2, etc., etc. But notice here, if it is also true for k and, so since it's true for 1 and 2, then it's going to be true for all integers by induction. Alright, let's finish off with last year's HSC question. Also dealing with the square root of 2 though, by coincidence. So here's our definition this time. It's nested surds. So A1 is root 2, A2 is root 2 plus root 2, A3 is root 2 plus root 2 plus root 2, and so on and so on and so on. There is the recurrence relation for this expression. So a way of writing would be that A squared is always 2 plus the previous term. Use mathematical induction to prove that every term is actually equal to 2 times the cosine of pi over 2 to the power of n plus 1, which I'm sure you looked at and went, yeah, well, of course it is. We're trying to prove then that an, remember when you start your proof, write down what you're trying to prove. This is what we're trying to prove. An is equal to 2 cos pi on 2 plus 1 for all positive integers. Prove it true in the first case. Okay, sub it. A1 is 2 cos pi on 2 squared, pi on 4 is 1 on root 2. We get root 2. So yep, it works for n equals 1. Now I see why that isolated one's there, because, fill in. Assume the result is true for n equals k. So this is what we're trying. This is what we're assuming. We want to prove k plus 1. That is what we want to prove. There's the recurrence formula, sub in. Okay, how do I get there? Well, that was by assumption, fair enough. Now I'm going to use double angle results. So 2 plus 2 cos pi on 2k plus 1 is actually the same as saying 4 times a half of 1 plus cos pi on 2 to the power of k plus 1, because that a half I could rewrite now to make it more obvious. 2 times pi on 2 to the power of k plus 2. In other words, that becomes cos squared. Okay, this is our double angle result rewritten. Okay. So it becomes 4 cos squared pi over 2 to the power of k plus 2. Well, a k plus 1 is equal to 2, because remember that was a squared. Therefore, a is 2 cos pi on 2 k plus 2. And I believe that is what we had to prove. So you have to use your double angle, all sorts of good stuff in this question. Hence it is true, etc., etc., etc. I'm pretty sure, yeah. There we go.